All right. Hi, everybody. Welcome back to our next installment of remote learning. I do have some good news for you. After this one that you're watching right now, there will only be one more after that, and then we will have a test on this stuff. And I'm looking at putting together a review session before that, either Monday or Tuesday. So be looking on Google Classroom for a survey about what times either do or don't work for you. So we can maybe do like a Zoom or a Google Meet review session, so you can ask me some questions. I know that's pretty important that we do that. So we will. I'll try and figure that out for you. Okay. Okay, so what we're going to be talking about today is logarithms, and that's a big fancy word for just what we're going to be talking about is the inverse of exponential functions. So for the last 3 weeks now, we've been talking just about exponential functions and what their graphs look like and how they behave and um, solving their equations. And we're just looking at the inverse of those now. So this is definitely related. We're going to start with a little bit of review on exponentials and what an inverse is, and then actually dig into what that looks like for this case. Okay. Okay. So like I said, we are going to do a quick review. I want to start by talking about inverses, where they come from. So the most basic thing that we talked about a long time ago is that a function matches an input to an output, right? Just kind of like a machine or like a pop machine. You push a button and the machine does its thing and your soda comes out. So the input is your money, and which button you push, the machine does its thing, and then we have an output, and that's your soda from a soda machine or a snack machine, whatever. Okay. An inverse matches an output back to the input that it came from. So on your soda machine, based on what pop comes out of the machine, you should be able to figure what button you pushed, right? So we can go back and forth. An inverse just takes the output and matches it back to the input that it came from. What does that mean for us? That basically means that x and y are going to get switched. That's the straightforward. What happens with an inverse? The x and the y get switched. You switch your inputs and your outputs. Okay, and that happens in tables, and it happens in equations, and it happens in graphs. They're all related. So when you switch x and y, it changes the table, it changes the equation, and it changes the graph. So a couple quick examples of finding inverses here. So example one, let's say we've got these x's, 1, 2, and 3, and they match up with these y's, 6, 7, and 8. And so to find the inverse, all we would have to do is what it says right here. Switch the x's and the y's. So the inverse, 6, 7, 8, instead of being under the y column, now 6, 7, and 8 are under the x column. And the 1, 2, 3, instead of being under x, now 1, 2, 3 is under y. We just took the x's and the y's and we switched them. That's it. Okay, and we can do this with equations too. Let's say we start with an equation like this. Y equals x plus 5. And so we want to find the inverse. So what do? Well, we do the same thing that we did in example 1. We switch x and we switch y. This is stuff that we've talked about before, just kind of trying to remind you what these things are. So that's exactly what we're going to do. We're going to switch the x and the y because that's what an inverse is. So there's the x where the y used to be, and the y is now in the x spot. X now equals y plus 5. Now, usually, though, we like to solve these inverses to get y by itself because that's how we had the first one. The first one had y by itself, so we want to get the inverse to have y by itself. And this one's pretty simple. It's only one step. If I want y by itself, all I need to do is minus 5 on both sides, minus 5 on both sides. And what do you get? X minus 5, and now we've got y by itself on the other side. Okay, so this would be, again, an inverse just with equations instead of a table. Inverses are just switching x and y. Okay, the last two things I want to remind you real quick. An exponential equation or function just means that x is in the exponent spot. This big old phrase exponential equation is like, oh, that's a mouthful. All it means is that x is in the exponent spot. It's not too scary. And here's an example to remind you too. Y equals 2 to the x. There's x, it's in the exponent spot. So this is an exponential equation. And the last thing on this review page is that graphs of exponential functions have asymptotes. Remember, asymptote, that's also a word that's kind of maybe big and scary, but it's not complicated. All an asymptote is a boundary line. A boundary line. And exponential graphs do have a boundary line. Okay, so inverses of exponentials, the graphs. Now we've reminded you what an inverse is. We've talked about reminding ourselves what an exponential is. Now we're gonna put those two things together. So the first video we watched, I gave you this function right here, graph the function f of x equals 2 to the x. Now we're going to do that again, but we're also going to graph its inverse, okay? So I'm going to make a table to make this graph, and I'm going to use all of these numbers as x. So I'm going to do 2 with -3 up here. And if I do 2 with -3 up there, then I get 0.125. If I do 2 with a -2 up there in the x spot, then I get 0.25. I just took all these x numbers and put them into this equation for you and already figured out what comes out. And these should make sense, right? 2, if we put in 2 for the x spot, 2 with a 2 up here, that's 2 squared. 2 squared is 4, right? And if we put a 3 up here, that's 3 2's, 2 times 2 times 2, and that's 8. So just took all of these x numbers and plugged them into the equation to get these numbers on the bottom. That's all I did, okay? All right, now we're going to take all these points and we're going to put them on our graph, right? So this one, like this one right here, 0, 1, it's going to go over 0 and then up 1. And then this one, 1, 2 from the center, that one will be over 1, up 2. And then like this last one, 3, 8, that one from the center is going to be over 3 and up 8. And there's that one, and there's all the rest of them too. I just took these points that are in the table up here, and I took those points and just made dots on the graph with them. That's all I did. Now I'm going to connect those dots. And this shape should look familiar. This is what we've been talking about for the last like 3 weeks. So, we'll get into describing the shape of this here in just a minute. And I did say that it has a boundary line, and so that's going to be this purple line right here, right? If you look at the blue curve, it gets really, really close to the purple boundary line, but it never actually touches it or goes past it. Okay, it can get as close as it wants, but it can never actually get there. All right, so I'm going to try and color code things throughout this whole video. Okay, so this blue, this is the exponential. This is the stuff that we already did starting 3 weeks ago. And I try to make my boundary line a different color, but also kind of use my art knowledge. Both of these are cool colors. So the purple goes with the blue. It's the boundary line for the blue because those are both cool colors. Okay, and then the inverse stuff is all going to be in warm colors. Okay, so just like we did in the last slide, I'm going to find the inverse just using this table. So to find the inverse, remember the one we just did, what did I have to do? All I had to do was switch the x's and the y's. So I'm going to take all these x numbers and put them down on the bottom with f of x, and I'm going to take all these numbers that are on the bottom and switch them up to the top in the x row. And that looks like this, okay? All I did, this is the inverse table, and like I said, all I did was take the top numbers and switch them with the numbers on the bottom, because that's what an inverse does, okay? Now, just like how I made this first graph, I'm just going to take all of these points and just make dots on the graph. So like this one right here, 2, 1. This third one from the end, this one's going to go over 2, up 1. And then 4, 2. That one from the center is going to go over 4 and up 2, and so on. And I'm just going to use these points to make dots. And there you go. There they are. Like I said, over 2, up 1. Over 2, up 1. There's a dot there. 4, 2. Over 4, up 2. There's a dot there. Okay? And they all match up. So now all I'm going to do is just make my graph nice by playing connect the dots. And there I've got a nice curve. Now, the one thing that is interesting is just like the blue graph, the original function, this one also has a boundary line, but it's not the purple one. And in fact, the boundary line for the red one does not even go side to side. It goes up and down. And that's this orange line right here, right? The red line will get really, really, really close to that orange boundary line, but never actually touch it. It can get as close as it wants, but it can never actually touch it. Okay, so that's kind of interesting that it also, because the blue one had a boundary line, The red one also has a boundary line because the original had a boundary line. The inverse, the red one, also has a boundary line. So let's compare these graphs. So all I want to do right now is talk about what the shape of these things are. And when we describe this stuff, all I'm really trying to do here is use words to say what it looks like. Like imagine someone gave you a painting of a person and asked you to describe it. What would you talk about? You would maybe talk about if they have facial hair or not. You would maybe say if they're wearing a hat or not. You would maybe say what their eye color is, right? If someone gave you a painting and told you to describe it, those are the things that you would talk about. And so all I want to do here is describe, that's all I'm doing, except in describing a painting, I'm just describing a graph. Okay, just what does it look like? We'll start with the blue one because this is what we're familiar with. This is what we've already been talking about and should kind of know. It starts out flat, then it starts to grow up, right? And then first it's growing a little, and then it starts to grow faster and grow faster and grow faster, right? And then by the end it's going almost straight up. It's growing very fast, okay? So now I want to compare that to what the shape of the red one is. The red one does not start flat, right? It starts out very steep. It's going up very fast at the beginning. And then what happens? It starts to flatten. It slows down a little bit. Something that's very, very important, and I think I'm actually going to circle this, is that it never totally flattens out. It keeps going up and up and up forever. Okay, so that's very important, is that it never totally flattens out. Because I'm sure some of you are looking at this graph and saying, oh, well, that just looks like a decay graph. And it's not. It's not a decay graph. It's slightly different. It looks similar, but a decay graph would have a boundary line at the top, right? And it would have basically a decay graph might have a ceiling. Okay, this one does not have a ceiling. It will keep going up and up and up forever. And so that does make it different. We're not talking about a decay graph here. We are talking about the inverse graph of this exponential. Okay, I'm going to jump back to the blue one here really quick. If we look at the blue one, we could plug in any number for x, right? Look at where x is. It's in the exponent spot. I can put, it's not like, dividing by 0. You can't divide by 0. There's no problem like that happening here. I can put in any x I want, right? Any number I want can go in the x spot. It doesn't matter. But that's not true for the inverse. If you look at all the inverse, all the inputs, every number up here in the x, they're all positive. Every single one of them, okay? And that is very special to these this inverse. That doesn't always happen. It's very special for this one that all of the inputs are only positive. All of your x's, they're all positive. They're all bigger than 0. Okay, the blue one has a horizontal asymptote. Remember, asymptote is just a boundary line. That's this purple line. So it has this purple boundary line. The original one does. And the inverse also has a boundary line, but we did already mention that it's this orange one. And instead of going to side, this one is going up and down. So the inverse has a vertical asymptote. So they both have a boundary line, but this inverse, its boundary line is vertical, straight up and down. So it is a little bit, it has one, but it's different. It's the opposite. Okay, so this inverse is so special that it has its own name, and it's called a logarithm. Okay, so we've done inverses before. We're just taking this inverse and giving it a name, and that name is logarithm. So we already noticed that all these x's none of them are negative, right? What about 0? Because we're going from 8, 4, 2. We've got a really small number right here, 0.125. None of them, not only are they not negative, but none of them are 0 itself either. So why can't x be 0? And that comes back to the original function, the 2 to the x here. In the original function, it doesn't matter what the exponent number is, right? If you look where this x is, it does not matter what that exponent is. Look, we did positives and negatives in that exponent spot, okay? And no matter what number we put there, we could never get 0 out on the bottom, okay? My challenge to you, if you don't believe me, is find me a number to put in that x spot right here, this blue equation, put a number in that x spot to that number, and you put it in your calculator, and you get 0. It'll never happen. And because we can't get 0 out of the blue equation, that means we can't put 0 in to the red equation. Okay, so that we're starting with the graph just to introduce this, but really what we're focused on today is the equations. The graph kind of helps us see, okay, so we're doing the inverse, and that's something we've done before. We can do that. Okay, we're going to bring this now to the equations. So exponentials that we've been talking about always look like this. Different numbers, but they all kind of look like this. Y equals b to the x. Now I'll give you an example. Like we just did, the graph of y equals 2 to the x. This is another one. Y equals 5 to the x. X is in the exponent spot, so this is an exponential equation. And we're talking about inverses today, and that's called a logarithm. We just mentioned that in the last slide, that this is just a special name for this special inverse. Okay, x equals b to the y. All I did was just take this right here and do what an inverse is. I just switched the x and y. That's what it means to do an inverse, right? So that's all I did. Just switch the x and the y. Okay, and for example, I'm going to take the example and do the inverse of that example as well. X equals 5 to the y. Just trying to do one that has an actual number in it instead of a whole bunch of letters, in case that helps anybody. Okay, I took this example, y equals 5 to the x, did the inverse. So I switched x and y. Now I got x equals 5 to the y. Okay, but like I said in the first slide when we reviewed inverses, usually though, we like to solve these inverses for y. We like to have y equals blah, 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 blah. So it's not so easy to do that with these ones. With the example in the review slide, all we had to do was do -5 on both sides, and boom, we had our inverse. It was that simple. Nice and easy, quick, done. Not so easy when our variables are up here in the exponent spot. Okay, so math people, if they wanted to get y equals like this, like we like to have, they had to invent a new way to write this this relationship, to write this equation. Okay, and it looks like this: y equals, that's what we want, equals log with little b down here in the bottom, and then x after the little b. So y equals log b to bx. Log is used because of the name logarithm. It's just short for logarithm, and so we just use the name in the new way that we invented to write this. Log just means logarithm. X and y are the same x and y from up here. That didn't change at all. They're just in new spots. And b stands for base. Okay, why does b stand for base? And it's because of where it comes from. If we look up here, when it was written with an exponent, right, there's no exponents in this log. This one that says log, there's no exponents anymore in there. But if we look up here, when we still had exponents, what's b called, right? Y right here, that's in the exponent spot. That has a name. It's the exponent spot. What is b called? B is called the base. And so it's the same b is up there, and it gets the same name because of where it comes from. Up here, it's the base. So here we call it the base. It's the same thing. Okay, so I want to explain what logarithms are, what the purpose of them is, so maybe we understand them a little bit better before I do a couple examples here. So I've mentioned a few times that we've been talking about exponentials for the last few weeks. Last week we started talking about solving them. Last week I think is the first time we talked about solving them. For example, we might have something like this: 3 to the x equals 81. And we want to figure out what x is, right? The question is, what number is in the exponent spot? And remember, what an exponent is, when you have an exponent, you got to multiply the base by itself. And how many times do you multiply by itself? Well, whatever the number is up there. So really, when we ask what number is in the exponent spot, really what we're asking is, how many 3's do I need to multiply to make 81? Okay. Logarithms put the exponents in its own spot to show that the exponent is what we're trying to figure out, right? In this equation up here, where is x? X is in the exponent spot, so that means what are we trying to do? We're trying to figure out the exponent. And that's why they invented logarithms, is to show, hey, this is the thing that I don't know, and it's the thing I'm trying to figure out, so I want that by itself. And that's why they invented the new way to write it. And there it is. Okay, log 3. That's our base up here, right? This expression, 3 to the x, the base is 3. And so it goes in the b spot because it's a base. So there it is, log 3. And then 81 is the answer up in the exponential version. So that goes right there. And what do we have by itself? The exponent. X is in the exponent spot, so there's x by itself. That's why they invented this, is because we are trying to figure out an exponent, and to show that, I want to put that exponent by itself. I want to be able to write that exponent by itself, and that's why they did that. This example right here, turns out the answer is 4. Log base 3, 81 equals 4. Why is the answer 4? And the reason that the answer is 4 is because you need to multiply 4 3s to make 81. 3 times 3 times 3 times 3 equals 81. How many 3s did we have to multiply? 4. Okay, let's do a couple examples. These are the only kinds of problems that you'll be seeing in your Go Formative homework. All of the other questions are just questions that are making sure that you've been listening to the things that we talked about so far and understand those. So a lot of it's just if you read the question, I give you the exact answer either out loud or it's typed on the PowerPoint. Every single one of those questions to start the Go Formative homework is just, it's either I say it exactly word for word out loud or it's typed word for word on the slide. Okay, but what we want to be able to do is we want to be able to switch back and forth between these two different ways to write this. We can write things as an exponential, like this one, x equals b to the y, or we can write it like a logarithm, y equals log b to the x. And we want to be able to take the blue one and translate it into the red one, or go backwards too. So first what we're going to do is we're going to start with the exponential, and we want to be able to write it in a log form. I'm going to do 2 examples of these. Okay, so this first one says 2 to the power 8 equals 256. So 2 is our base, so that's going to go in the B spot right here. 2 is our base, so that's going to go in the B spot. 8 is our exponent, and remember when we write logarithms, the exponent should be by itself. So that's going to go in this Y spot, and then equals 256. That's going to go in there's only one spot left, that's the X spot. So what does that look like? Log 2, base 2, 256 equals 8. 2 is the base, so it went in the B spot, the base spot. 8 is the exponent, and now the exponent is over here by itself where it should be, and then 256 is the only other number. It's 250. It goes in the X spot right there. Okay, I'll do another one. So let's say we start with 16 with 3/4 in the exponent spot equals 8, and some people might freak out and be like, well, what do I do now? There's a fraction there. It doesn't change what you do at all. What's our base? 16 is our base, so that's going to go in the B spot. 3/4 is our exponent, so that's the number that should be over on the other side by itself in the Y spot, and then equals 8. So 8's the last number, so that's going to be the X. And so it looks like this. Log base 16 because 16 is our base to start with, and then we've got the exponent 3/4 by itself, just like we want, and 8 is in the X spot, so it goes right there after the little 16. Okay, I did say that we want to be able to go both ways. We want to be able to go we want to be able to translate from exponential to logarithms. We also want to be able to translate from logarithms back to exponentials. So that's what this next example is going to focus on. Write each equation now in exponential form. So this one, I'm going to do 2 of these as well. The first one we're going to do, log base 8, 512 equals 3. Okay, so remember 8, that's in the B spot. It's in the B spot, so that's our base. So when we write it on the other side, 8 better be in the B spot. We have 3 by itself. What number goes by itself when we write a log? The number that goes by itself is the exponent, so we should have 8 to the power 3 8 to the power 3 equals 512. The 512 goes by itself now. I usually like to think of which number is my base, which number is my exponent, and then there's only one spot left for the third number. Let's do another one. Okay. Log base 9, and then we got the fraction 1 over 81 equals negative 2. Okay, so we already talked about how don't freak out just because there's a fraction. You're literally just moving numbers around, so just move it at like it wasn't a fraction. And now we've got a negative in here too, but more good news, it doesn't matter. You're just moving pieces around and putting them in a new spot, so just it does not matter that the negative is there. Just bring it with, okay? So what's our base? Our base is 9. Our base is 9. 9 is in the B spot, so that is our base. And so on the other, when we translate, 9 better be the base again, because that's what it is. And then what number is over here by itself? Negative 2. So that means that's when we write a log, the number that's over there by itself is the exponent. So we have a base of 9, and it should have an exponent of negative 2. So we have 9 with an exponent negative 2 equals, what was the big number in the log? It was that fraction, 1 divided by 81. Okay, there you go. 9 with the exponent negative 2, boom, equals 1 over 81. Okay, that's all you got to do. All right, that concludes our lesson for today. As usual, just answer your questions that are posted on GoFormative, and that's all you got to do. Like I was, just another reminder once again, be on the lookout on Google Classroom for a survey of what times are going to work for you or not going to work for you if we try and do a review session through Zoom or something like that. Okay. Just want to make sure I get you the help that you need, give you a chance to ask some questions, because I know email's not always the best. So sorry I couldn't do that a lot, but definitely trying to get one in for you before the test so you can ask me some questions. Other than that, that's all I got. Everybody take care of yourself, stay positive, and see you next time.